Welcome back to EDUHUNT IIT and NEET foundation classes. This is Sukumar, your chemistry mentor. See, in the previous video, I explained how to determine or how to apply the VSEPR theory for a given type of formula to determine the geometry. Like we have taken AB2 type and how to determine and what are the possible geometries to that type. And next we have taken AB3 type and what are the possible geometries we discussed. And in that AB3 type, we have taken AB to E like that. That E means one lone pair. Yes. Okay. I hope you understand that concept. Okay. That's simply the application of VSEPR theory. Now in this video, I'm going to take few examples from that list only. On special note, I'm going to take some examples from that list and I am going to discuss few important points regarding their geometries, the special points regarding their geometries. Okay, let's start. See, for suppose in this type called AB5 type, AB5. What I mean by AB5 type? AB5 type means there is central atom, there is 5 electron pairs. The number of electron pairs is 5. And all the pairs are bond pairs, 5 bond pairs. That means I can say electron pairs are 5. Among the 5 electron pairs, all pairs are bond pairs only. How can you say that? See, if there is one lone pair, one or more lone pairs, each lone pair we are going to indicate with the capital letter E. E. I explained in the previous video. Now in this formula there is no E. Okay, and there is a 5 bond pairs. Okay, all 5 electron pairs, all the pairs are bond pairs only. That means lone pairs are going to be 0. And I explained in the previous video that whenever there is a 5 electron pairs, whether they are lone pairs or bond pairs, whenever there is 5 electron pairs, the geometry suggested by Sidgwick and Powell is a trigonal bipyramidal. Trigonal bipyramidal. Trigonal bipyramidal. How it looks like? See, central atom A, and there is first trigonal part like this, B, B, B. For better understanding of the trigonal part, I am going to make some dotted line view. See, these dotted lines are not bonds. Okay? Yes. This is the trigonal part I am talking about. Now, see, above the plane, one bond pair. Below the plane also one bond pair. See, on the board, this plane may look like this, okay? But actually, this is not on the board. This is like this. This plane, this trigonal planar part is not like this. This is like this. That means above the plane, one bond. Below the plane, one bond. Trigonal bipyramidal. So, towards upside, you can find a pyramidal shape. And towards downside also, you can see a trigonal bipyramidal, trigonal pyramid part. Okay? Okay, fine. Sir, what's special about this, sir? See, in this trigonal bipyramidal part, all the corners are not of same type. In this trigonal bipyramidal part, all the corners are not same type. There are 2 types of corners. See, you can find 5 corners, but all the 5 corners are not of same type. They are of different type. What are the types, sir? These three are called equatorial. These three, this is equatorial position, this is also equatorial position, equatorial, and these two are called axial positions. These two are axial, that means axial, first thing. And what is more important point, it may look like a regular symmetrical structure, but it is, in one way you can say that it is not regular, because in this structure all the bond angles are not same. There are two types of bond angles. See, one type of bond angle, see, this bond angle is going to, this is going to be 120 degrees trigonal planar bond angle. See, if I draw the trigonal part like this, this is the trigonal part, right? Trigonal planar part, and the bond angle is going to be 120 degrees. And I told you already that this is not like this, this is like this. Now, towards the upside there is a bond, right? Now, what is the bond angle between these two? This is going to be 90 degrees, na? 90 degrees. So, two types of bond angles. So, 120 degrees and 90 degrees. Okay? Now, this is just a model, AB5 model. Now, I am going to take a particular example, real example with this type of geometry. That was nothing but pcl5. That was nothing but pcl5. pcl5. And especially I am talking about pcl5 gaseous molecule, pcl5 gaseous. That means in gaseous state. Gaseous state. That means pcl5 in solid state is going to be different. Now I am talking about pcl5 gaseous state. So what happens here, sir? And what model it is according to VSEPR theory, in what way it comes? See, you can approach like this. After this video, I am going to explain how to determine the geometry or shape with a formula also. I will give you a trick also. But now, see, this is pcl5. You know very well, phosphorus belongs to 5th group, that means 15th group, nitrogen family. And in that family, all of the members will have 5 electrons in their valency shell. 5 electrons in their valency shell. You make 5 electrons, 1, 2, 3, 4, 5. Okay. Now, and there is it's a normal common sense fact that chlorine as a side atom, when chlorine is central atom, that's different. Chlorine as a side atom can form only one bond. That means valency is 1, chlorine valency. So, 1, 2, 3, 4, 5. Okay. Don't bother about the geometry now. Okay. First make the structure, make the connections clear. Okay. Is all the connections are clear now? Yes. Phosphorus is the central atom. There is 5 side atoms and 5 bond pairs. No lone pair left. Now it comes under what category? This category, na, AB5 type. That means pcl5 is a trigonal bipyramidal structure. pcl5 is a trigonal bipyramidal structure. Chlorine, chlorine, chlorine. Now this is the trigonal part I am talking about. towards upper side, this is one pyramid, Cl and the, okay. I'll repeat, all these positions are not same. These 3 are equatorial positions and these 2 are axial positions. Okay, and there is 2 kinds of bond angles. Okay, in this trigonal part, this bond angle, all this bond angle or this bond angle, you can say that is 120 degrees bond angle, and the bond angle between this bond and this plane, this is going to be 90 degrees bond angle. Okay. Now, with the difference in that bond angle, see, I am explaining there is 2 kinds of bond angle. Okay, fine. In that aspect, you can say that this pcl5 is not a regular structure. Okay, fine. It is not a regular structure. Fine. There is 2 different bond angles. Okay. And I am again saying all the corners are not same. There is two different corners. 3 equatorial corners and 2 axial corners. Okay, fine. So I am making 2 statements. But now what? See, in this pcl5 example, it doesn't make any difference if there is two types of corners, two types of bond angles. It doesn't make any difference because all the atoms are chlorine only. All the atoms are chlorine only. Okay. Whether it is equatorial position, or axial position, it doesn't make any difference to us because all the positions are occupied by chlorine only. Now the question arises, sir, what happens if there is two different types of atoms in this trigonal bipyramidal part? Or what happens if there is one lone pair among these 5 pairs, among these 5 electron pairs? What happens if there is a lone pair? Now the question arises, if there is one lone pair, at what position I should give? Do I give the lone pair? Should I give the lone pair to the equatorial position or axial position? That's the question, na? Yes, I am going to discuss that now. Okay. And one more thing, I said this pcl5 is in gaseous state. Sir, what about solid state? See, in solid state, I'll take the next page. In solid state, pcl5 is going to be ionic species like pcl4 plus and pcl6 minus. And if you apply the concept, it is going to be tetrahedral geometry, and this is going to be octahedral geometry. Okay, that's it. Now I am going to take one particular example in which there is a trigonal bipyramidal geometry, but all the corners are not occupied by the same points. Okay, all the corners are not occupied by the same atoms. Okay, one of that kind of example is I can take clf3. Okay, now what kind of molecule or what category this particular molecule belongs to? The previous video I made. See, in the previous video I have explained AB2 type, AB4 type, AB5 type. You tell me what category this belongs. See how to determine that. Chlorine, the valence electrons in chlorine belongs to 17th group. The number of valence electrons in halogens is 7 only. So 1, 2, 3, 4, 5, 6, 7. Okay, and you know, as a side atom, fluorine or any halogen can form only one bond. So use this electron to bond with fluorine, single bond. Use this electron also. Okay, don't bother about the geometry now. Okay, after completing this structure, then propose the geometry. Okay, fine. Now total how many electron pairs you find here? Lone pair, bond pair. That means 3 bond pairs plus 2 lone pairs, a total of 5 electron pairs. Now what kind of formula this is? 3 bond pairs means AB3. 2 lone pairs means E2 type. Now if you forgot, please go back to that previous video, okay, at which I have explained how to determine the geometry when the molecule is AB3E2 type. Okay, yes, now fine. Let's now, so whenever there is 5 electron pairs, the minimum geometry which gives minimum repulsions is trigonal planar. Yes, trigonal planar. That means trigonal part. Sorry. I said trigonal planar. It is trigonal bipyramidal. Yes. Yes, this is the geometry. Now the central atom is chlorine. And trigonal bipyramidal geometry means, first of all, I need to make how many how many corners? 5 corners, right? Yes. One above and below. Okay. Now the question arises, these 5 corners, I told you already, these 5 corners are not same. Among these 5 corners, these 3, 1, 2, 3, these 3 are equatorial corners and these 2 are axial corners. Now the question arises, among these 3 bond pairs and 2 lone pairs, where should these lone pairs will go? Shall I give these 2 lone pairs here, here, or here, 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 here? Where? What is the best structure or what is the original structure? Okay. So first of all, we should think about the possibilities. Then we are going to decide or determine which structure is stable, which is more stable. Okay, that will be the correct structure. So first of all, what are the possibilities? On first possibility, I am taking one lone pair here. I am taking both the lone pairs at axial positions. I am taking both the lone pairs at axial positions. Then obviously, fluorine, fluorine, fluorine. This is one possibility I can have. Next, chlorine. I will make trigonal bipyramidal geometry first. Now, what is the another possibility I can have? See, take one of the fluorines. Among these 3 fluorine, see, these 3 corners are of same type. 3 are of same type. Okay, 3 are of what type? Equatorial part, no problem. So, take this one of the equatorial fluorine, this or this or this, anyone. I will take this one of the fluorine and put it in the axial position, and take this axial position lone pair, I will put it in the equatorial. So, and rest of the places I will make same. This is one possibility. This is one kind of possibility. Okay. And another kind of possibility, I will take this fluorine. I'll take this fluorine also here, and I take this lone pair to the equatorial position. Another possibility. First of all, I'll make the trigonal bipyramidal geometry with the central atom chlorine. Again this lone pair also I am taking to the equatorial position. So now in this structure or in this geometry, both the lone pairs are at equatorial, and rest of the 3 fluorines are fluorine, 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 like this. Fine. Now the question arises, among these 3 structures, let us say this structure as A, this as B, this as C. See, among these are the 3 possibilities on paper. These are the 3 possibilities we can draw on paper. But in reality, in our real life, which structure, which geometry exists depends upon their stability, depends upon their corresponding stability. So, what is stability? Simply you can say, having the minimum possible energy is the stable state. Okay. Among these 3 structures, the structure with the minimum energy, again I am telling you, among these 3 structures, the structure with the minimum energy is most stable. I will write here, structure with minimum energy is stable, most stable, is most stable. Okay, fine, sir. Okay, fine, sir. Okay, among these 3 structures, you said that the structure with the minimum energy is most stable. Now you ask, how to determine the energy? See, more repulsions, more energy, less repulsions, less energy. Less repulsions, or I can say less, not less, I can say minimum repulsions. Okay, you can't completely avoid repulsions. Okay, the geometry is, you are making the geometry with the electron pairs only, whether lone pairs or bond pairs. So you can arrange the electron pairs in such a way, you can arrange the electron pairs in space in such a way to have minimum repulsions. Okay, yes. So structure or geometry with minimum repulsions is most stable. Okay. So, among these three structures, to find which structure is correct for clf3, which structure is correct for clf3, we need to determine in which structure there is minimum repulsions. Okay. And how to determine, what point to apply to find out in which structure there is minimum repulsion? Yes, again VSEPR theory. In VSEPR theory only, proposed or developed by Nylander and Gillespie, they said that lone pair repulsion is more than lone pair bond pair repulsion, right? Lone pair repulsion. That means the repulsion between two lone pairs. Here two important points, all right. The repulsion between lone pair and lone pair is going to be more than the repulsion between a lone pair and bond pair. And the repulsion between lone pair and bond pair is going to be more than repulsion between two bond pairs. Keep that in mind. This was given in VSEPR theory postulate only. Now, another point you have to consider here is, in this geometry, there is two kinds of bond angles. Okay. One is 120 bond angle, 120 degrees. Another one is 90. So, I can say that electron pairs, that means whether they can be lone pair or bond pair, electron pairs at 120 degrees, electron pairs, or I can say electron pairs at 90 degrees causes more repulsion than electron pairs at 120 degrees. Okay. Do you need any explanation for that? Simply, if the two pairs, see, I said EP means in my view, what is EP? Electron pairs. Okay. Electron pairs at 90 degrees causes more repulsion than electron pairs at 120. What happens when the electron pairs at 90 and what happens electron pairs at 120? See, compare it to electron pairs. See, consider this has an electron bond pair. Let us say bond pair. This is also bond pair. Now, two bond pairs are at 90 degrees. Okay, they have their own repulsion. Now, increase the bond angle to 120. Now, what happens? More bond angles means the bond pairs are very much far away, na? They move far away, na? So, repulsion decreases. So, bond angle increases, repulsion decreases. Bond angle increases, repulsion decreases, and stability increases, right? So, this is the order for what? Repulsion. And this is also for what? This is also for repulsion. Okay. Now, try to apply this concept. See, simply we are going to determine in which structure there is minimum repulsion. See, in the first structure, it may seem to be very regular or very symmetric structure because all the fluorines are at equatorial corners and one lone pair is on the top, another below. So, and the bond angle between the lone pair and lone pair is going to be 180, na? So, it looks like lone pairs are at very far away. But the point is, here you can say, I told you already, this part, this middle part, this trigonal part is not on the board plane. This trigonal part is not on the board plane like this. This is just like this. Now you tell me, what is the angle between the lone pair and the corner fluorine, or lone pair or the bond pair? What is the repulsion? What is the angle between this lone pair and this bond pair? 90 degrees. Na? So, of course, lone pair, bond pair repulsions are not very much high, not very much low. They are middle. But the point is, this kind of lone pair, bond pair repulsions here is how many you count? Lone pair, bond pair, lone pair, bond pair, lone pair, bond pair on towards the top. From bottom, lone pair, bond pair, lone pair, bond pair, lone pair. There is 6 lone pair, bond pair repulsions operating. Okay, there are 6. They huge. That means it's a big number. Okay. So of course the lone pair, bond pair repulsion is not very less, not very high. Okay, it is moderate repulsion, but still the number is high. That's why this is not going to be the stable structure for clf3. See, the point is, among these structures, the stable structure is found to be practically. So, see, scientists have determined the stable structure practically this one. They found that clf3 exists like this. But we are going to explain theoretically why this is stable among the 3. Okay. Now, I ruled out one structure. Why this is not going to be the stable structure for clf3? Because of 6 lone pair, bond pair repulsions. 6 lone pair, bond pair repulsions, and all are at 90 degrees. Okay, fine. Now compare these two. It's going to be very simple. See what happens here. Here the lone pair repulsions, right? Here there is one lone pair repulsion, lone pair repulsions at 90 degrees, and you know very well that lone pair repulsion is the highest. It is having higher repulsion, right? Repulsive power, higher repulsive power. So lone pair repulsion is at 90, but here the same lone pair repulsion is at 120. So the lone pair repulsion is at 120. Okay, they are very much far away. That is going to be stable. And one more thing, what about the rest of the flow? So this bond pair repulsion at 90, bond pair repulsion at 90. See, among these, bond pair repulsion is at the repulsion is the minimum one. This is the least one, right? Repulsive power, according to repulsive power, bond pair repulsion is last. But that minimum repulsive power is, we put it at what? 90 degrees, right? So this bond pair repulsions we kept at 90 degrees. And the maximum repulsion showing lone pairs are lone pairs. Lone pairs are showing maximum repulsions, but we kept at the maximum possible distance. We kept that lone pairs at maximum possible distance, and we kept that bond pairs, which causes, 2 bond pairs causes minimum repulsions, we kept that at 90 degrees. Okay, so that is going to be the stable structure for clf3. So this is the one way of explaining. This is one way of explaining why clf3, among the 3 possible structures, why clf3 adapted this structure. I can explain one more possible way. Okay, so this explanation is based on repulsions between lone pair and bond pairs according to VSEPR theory, and by the way of hybridization, by the concept of hybridization also we can explain this. See what happens here. clf3 why this structure is the best structure means, see what happens here. For this trigonal bipyramidal geometry, what is the possible hybridization? 1 s orbital, 3 p orbitals, and 1 d orbitals, right? So actually I think in that hybridization video I explained that in this for this structure or for this geometry, the possible hybridization is sp3d hybridization, sp3d, right? But the point here is, it is not just like sp3d hybridization. See, if it is just a simple sp3d hybridization, all the corners should be same, right? You know very well what happens when sp3d hybridization. There is 5 hybrid orbitals you are going to get. Okay, among that 5 hybrid orbitals, all orbitals are going to be same na, because 5 atomic orbitals are intermixing. You are going to get 5 hybrid orbitals, all are going to be same. 5 sp3d hybrid orbitals. And in that hybridization concept, I have explained that all 5 hybrid orbitals are of same type in general, right? See, if all the 5 hybrid orbitals are of same type, then why you get 2 different corners? I said these 3 are equatorial and these 2 are axial. So, it is this hybridization is not just simple like this sp3d. What happens here is to form 3 equatorial positions. To form 3 equatorial positions, let us say this is S, Px, Py, Pz, and let us say this is dz square. Okay, I hope you know the d orbital, rest of the d orbitals. I hope you know dxy. Let me write dxy, dyz, dx square y square, and dz square. I hope you know that. Okay, I am taking this dz square part. Now what happens? To form 3 equatorial orbitals, to form, let me explain first. Let me write those positions first. 1 equatorial. To form these 3 equatorial orbitals, equatorial hybrid orbitals, 3 atomic orbitals must intermix, na? Yes. What are they? 1 s orbital, 1 px, and py. When 1 s orbital intermixes with px and py, 3 orbitals are intermixing. You are going to get 3 hybrid orbitals. What are they? 3 sp2, 3 sp2 hybrid orbitals. That means this is the sp2, this is sp2, and this is also sp2. Okay, fine. Now, how these 2 orbitals came? These 2 orbitals came. These 2, I said these 2 as axial. How these 2 axial orbitals came? See, to have a axial orbital, axial hybrid orbital, the intermixing atomic orbital must have that characteristic feature of the z-axis, right? So that's why this pz intermixes with dz square. Okay. Now 2 atomic orbitals intermixing. When 2 atomic orbitals intermixes, you are going to get 2 hybrid orbitals, right? What are they? 2 hybrid orbitals. What type of? Pz, dz. Okay. So that's how there is 5 hybrid orbitals. A total of 5 hybrid orbitals. 5 hybrid orbitals. Now the question is, you have taken chlorine, equatorial, axial. Careful, very much careful. This orbital is having sp2. That means all the 3 equatorial orbitals are having s character. But in the axial orbitals, that is just by pz, right? P orbital, that pz and dz square. That hybrid orbital is having pd character, no s character. Both the axial orbitals are having no s character. Now what happens if there is no s character? See, you can say more s character means more electronegativity. Always remember, more s character in the orbital means more electronegativity. More electronegativity means more power to hold lone pairs. Okay. And one more thing. If the approaching atoms, if the side atom is electronegative like fluorine, fluorine will prefer first axial positions only. Why? Because fluorine is electronegative, and that fluorine is going to choose less electronegative orbital because fluorine is electronegative. So, or I'll explain here. So, if this is central atoms, side atoms, see, first of all, if I have one fluorine, the first fluorine will prefer axial position only, and now supply another fluorine. The another fluorine also prefers axial position. Why, sir? Why, sir? Do remember, more electronegative atom prefers less electronegative position. More electronegative atom prefers less electronegative position. Okay, you supplied one fluorine, it has taken this less electronegative axial position. You supplied another fluorine, it has taken another. If you supply third fluorine, then for that fluorine no option, it has to take one of the equatorial position. No option, no option. Yes. Now what happens to the lone pairs? Lone pairs prefers axial positions. Why? Why? Because in this axial bond, what is the hybrid orbital? sp2. S character is there. S character means more electronegativity. More electronegativity means more tendency to hold the electron pairs. So that's why lone pairs will prefer, both the lone pairs will prefer axial positions. Okay? Are you getting the point? Yes. See, shall I explain one more example? Yes, fine. See, let us say XeF2. I hope you know this is going to be linear. But how? Let me tell you. Xenon. What is the total number of valence electrons in xenon? 8. You know very well, it is inert gas, zero group element. 1, 2, 3, 4, 5, 6, 7, 8. Fine, fine. And as a side atom, halogen can form only single bond. Yes. Side atom, as a side atom. Now use this electron to bond formation. Use this electron also. Okay. First of all, I am making connections. Now check how many bond pairs and how many lone pairs. One lone pair, another lone pair, 3 lone pairs. See, 3 lone pairs plus 2 bond pairs. 2 bond pairs. 3 lone pairs, 2 bond pairs. A total of 5 electron pairs. A total of 5 electron pairs. Whenever there is 5 electron pairs, then the geometry is going to be trigonal bipyramidal. Xenon is the central atom. Draw the geometry trigonal bipyramidal. But the point is, so in these 5 corners, 3 corners are equatorial, and 2 corners are axial. Now what happens? This lone pairs prefers equatorial positions. I told you already, lone pair prefers equatorial. Why? At equatorial position there is S character. One lone pair, another lone pair, third lone pair. And obviously the more electronegative atom fluorine prefers axial positions. So the electron geometry is going to be trigonal bipyramidal. But I told you in the previous video, the molecular geometry shape, to determine the molecular geometry or shape, you have to you don't consider the lone pairs. Now it is going to be linear geometry, linear shape is going to be linear. Okay? Yes. Now similarly, what happens? This sf6 sulfur hexafluoride, what kind of category it comes? It belongs, see, sulfur valence electrons 1, 2, 3, 4, 5, 6. You know, sulfur belongs to 16th group, 6 valence electrons. Fine. Okay. Then you know very well, as a side atom, halogen can form only one bond. So 1, 2, 3, 4, 5, 6. Fine. You made the connections. Now think about the electron pairs total. 1, 2, 3, 4, 5, 6. 6 bond pairs, 0 lone pairs. That means 6 electron pairs. Whenever there is a 6 electron pairs, the geometry is going to be octahedral. So sulfur is the central atom. So try to make the octahedral geometry. But the point is, like that previous trigonal bipyramidal geometry, this is not going to be different corners. Here in octahedral structure or octahedral geometry, all the corners are of same type. Student may get confused. because they remember that pcl5 structure. Similarly, sometimes student may think these two are axial, these are equilateral. No, 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 no. Here all corners are of same type. All corners are of same type, and I hope you can determine the hybridization also. How many total? Steric number S is going to be 6 sigma bonds, 6 sigma bonds plus 0 lone pairs, 6. So, it is going to be sp3. When the steric number is going to be 6, then sp3 d2 is the hybridization. All corners are of same type, fine. All corners are of same type, and all bond angles are of same type generally, okay, 90 degrees. So, this bond angle is 90 degrees, and this bond angle also, bond angle between these two also, okay, that is also 90 degrees, and 90 degrees bond angles, okay. So, if you want, you can take a bond angle like this, but the point is from the between the corners 90 degrees, between these two 90 degrees, between these two 90 degrees, like that, 90 degrees bond angles, okay. Yes, I will explain. See, for suppose if you take SF, if you take the geometry now like this, there is no equatorial, no axial. See, for suppose I will make the dotted lines like this, I will make the dotted lines like this. So, do not take these as equatorial, these as axial, okay. So, these two are octahedral only. So, in octahedral geometry, all the corners bond angles are going to be same only. So, then fluorine occupies all the corners with same ease, okay. Okay, I hope you understand. Let us meet in the next class. Thank you.